We're still diagramming where our electrons can be found, except now we're using a little different notation, okay, or a different way of diagramming. And this is called orbital notation. So you need to know the difference between electron configuration, which is 1s, 2s, 2p, all that kind of stuff, and orbital notation, which this is like drawing arrows to represent our electrons. So if I say on a test, give me the orbital notation for this element, you need to make sure that you're drawing these arrows like we're going to do it. If I say give me electron configuration, you're giving me 1s2, 2s2, all that kind of stuff. Okay, so there is a difference between these. Okay, so when we're drawing out these orbitals, we're drawing lots of lines and lots of arrows. So any line that is left blank, like this, means we have an orbital that has no electrons in it. Okay, one electron has one arrow. That means our electron contains our orbital contains one electron, and an orbital containing two electrons has two arrows. Okay. How many individual electrons can an orbital hold? Only two, right? Only two. So every time we draw an orbital, it can hold a maximum of 2 electrons. Why do you think they are written this way? Yeah, kind of the charges. More specifically, Andrew, what is it? The spins. Good. So one of them is spinning a positive direction, one of them is spinning in the negative direction. And I will tell you, it doesn't make a difference if you choose to draw the down first and then the up. It makes no difference as long as you're consistent throughout your whole diagram. So every electron would have to have the first one pointing down if you were going to do it that way. I rarely draw it that way, okay, if ever. And usually when I draw electrons, it's just a kind of a half-headed arrow, okay? That's the way you'll see it most times, but I can't do that in PowerPoint, so that's how it goes. Okay, so you'll see electrons usually with just a half arrowhead. Okay? I don't care how you draw them. Okay, so this is called Hund's rule, which tells us that orbitals of our energy have to be occupied by one electron before you can occupy by two. So orbitals of equal energy have to be occupied by one electron all the way across before we can go back and double them up. Okay, and this will make more sense when we start drawing it out. All electrons in a singly occupied orbital have to have the same spin state. So that's what I'm saying. When you draw your electrons, if you draw them up first, they all have to be drawn up first. And then you draw them in the opposite direction when you go through and fill them back in. Okay, so let's look at nitrogen. Okay, give me the electron configuration for nitrogen, which is 1s2, 2s2, that kind of thing. Okay, give me the electron configuration for nitrogen. One S2, 2s2, 2p what? 2p3. 3. We stop right here at nitrogen, and nitrogen only uses 3 of those electrons. The p orbital could fit 6, right? But nitrogen only uses 3 of them. Okay, so now it's orbital notation I'm going to draw over here. They represent exactly the same thing. It's just 2 different ways to draw it. So for orbital notation, we're going to draw out our individual orbitals. So the first orbital is the 1s orbital. Okay, and I'm just going to write 1s under there. Second one is 2s. Okay, what's the last kind of orbital that we have? 2p. So can I draw it like this? Or should I draw it like this? Right? What's the difference between those things? Do you know what the difference is? How many electrons can each orbital hold? 2. So if I just make one big orbital for the p's, right, that could only hold 2 electrons, and I need it to hold 3. So when I draw my p orbitals, I'm going to split it up into 2s, right? The p orbital has 3 different parts to it. Each of those could hold 2 electrons, which gives us a total of 6 within that p block. I'll show you, watch. So the 1s orbitals are full, right? Because they are, that can hold 2, so it has 2. So we're going to go 1, 2. Right, we're going to fill all the 1s orbitals before we go back and fill anything else. So the 2s orbitals, those are occupied also. So we fill those. So right now, how many total electrons have we accounted for? We've done 4, right? We need to have a total of 7. So now 2p3, we go back to this rule. Orbitals of equal energy, which are the 2p's, must be occupied by 1 electron before any orbital is occupied by a second. So this is what we're saying. We go 1, 2, 3. Okay, so don't write down what I'm going to do next. I'm showing you this is the incorrect way to do it. Right? That's not how it works. We have to fill all the way across, and then we could come back if we needed to for more electrons. Right? If we needed to do oxygen, we would come back and add our electron there. If we wanted to represent fluorine, we'd add it here. If we wanted to represent neon, we'd add it there. Does that make sense? But nitrogen only has 3 electrons found in that p orbital, so that's how it looks. We have to fill across, and then we can come back. And that rule only really applies to the p orbitals and the d orbitals and the f orbitals, right? The s orbitals only have 2, so if you, by the time you go across, you're already coming back, right? It's only 1 of each. You don't have to write the electron configuration first, but if that helps you put it into orbital notation, that's fine. You don't have to write both of them. Okay, boron is part of what block? The 2p, right? So we know we have to draw all of the orbitals up to that point, right? The 1s orbitals, are they full? Yes, right? We have to fill all those ahead of time. The 2s orbitals are full. How many electrons are found in the 2p block? Just 1. So can it go anywhere on any of these? Can I put it here?
Wait, why would you have to put all 3 on?
That's right. So we can't just leave it as 1, because that would make us think that the 2p orbitals only hold 2 electrons, when really we know they hold 6, but there's a bunch of unoccupied space in that p orbital.
The number of arrows always add up to the top.
That's right. The number of arrows should always add up to the number of electrons.
Would you take one stop and we go 2p, 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 just
Yeah, I only want 1 2p.
Okay.
Questions here? Okay. Try fluorine on your own. Okay, so on fluorine, it's really important that we fill in this order. 1, 2, 3, then we come back and fill the other ones. Okay? We're not just filling them as we go, right? We're going all the way across, and then we're coming back. Okay? if you know exactly how many electrons, like I get it if you would just go across, but as we get a little bit more intense and we get bigger orbitals, you could catch yourself, and that's a silly time to make an error, right? It's unnecessary to make that error. So just get used to going all the way across, then coming back within an orbital. Okay, try neon. Actually, no, I don't want you to try neon. I want you to try nickel. So nickel is a lot more than we've been dealing with so far, so you're going to need to give yourself a little room. Nickel has an atomic number of 28.